Welcome to The Explainer. Our whole goal here is to take big, complex topics and, well, explain them in a way that just makes sense.
Have you ever really stopped to think about that? How does your phone know it's you? Or how does a self-driving car see a person crossing the street? Well, today, we're going to peek behind the curtain and explore the amazing tech that lets machines see the world.
All right, so first things first, when we talk about teaching a machine to see, it's not really one single thing. It turns out computers see in a few different ways, and they solve different kinds of visual puzzles.
Okay, so there are two main jobs here. First, you have image classification. This is pretty straightforward. You show the computer a picture, and it tells you what the main subject is. This is a cat. Simple. But then you've got object detection. This is way more advanced. It's not just about what's in the picture, but where it is. It'll actually find multiple things and draw little boxes around them, saying, okay, here's the cat, and over here, that's a dog.
So, how in the world do they pull this off? Well, the magic is inside something called a neural network. And yeah, it's kind of modeled after our own brains. So let's crack open this digital brain and see what's inside. All right, the most basic building block is the artificial neuron. Just think of it like a tiny little switch or a decision maker. It gets a bunch of input signals from other neurons, adds them up, and then has to decide, is this important? Should I fire and pass this message on? Now the connections between these neurons are absolutely key. They aren't all equal. Each connection has a weight, which is basically a number that says how strong or important that connection is. And this is the cool part. The entire process of learning for the network is really just about adjusting these weights, getting them just right. So what makes a neuron actually fire? That's where something called an activation function comes in. It's basically a mathematical gatekeeper. The neuron gets all this input, and the activation function looks at the total and decides, yep, this is strong enough, let it through, or nope, not important, block it. This little gate is what allows the network to learn really complex, messy patterns, not just simple straight lines. Okay, so you take all these neurons and you stack them up in layers. It all starts with the input layer. That's where you feed in the raw data, like all the individual pixels from a picture. Then that data gets passed through what are called hidden layers. This is where the real magic happens, all the heavy-duty computation and pattern finding. And finally, you get to the output layer, which spits out the final result, like saying, hey, that's a cat. All right, so we have the parts, but how does this thing actually learn? It's not like it just memorizes a bunch of photos. No, it's this really cool back and forth process of trial and error, all driven by math. Step one is called the forward pass. This is basically the network's first guess. You give it an image, let's say a picture of a cat, and the information flows forward through all the layers. At the very end, the network makes a prediction. It says, okay, based on what I know right now, I think this is a dog. Whoops, it got it wrong. So the next step is to calculate how wrong it was. This is the error. And this is where it gets really clever. The network then takes that error information and sends it backwards through the entire system. This is called backpropagation. And what backpropagation does is incredible. It's like the network is an investigator, going back and figuring out which connections, which weights were the most to blame for the mistake. Then it tweaks those specific weights just a tiny bit so that next time it's a little less likely to make the same error. It just does this over and over and over. Guess, check your mistake, and adjust. The fancy name for this whole process of minimizing the error is gradient descent. I love this analogy. Think of it like you're standing on a hill in a super thick fog, and you want to get to the very bottom of the valley. You can't see it, but you can feel which way is down. So you take a small step downhill. Then you feel again and take another step downhill. That's exactly what the network is doing. It's always taking a small step in the direction that makes its errors smaller and smaller. Now, when it comes to images specifically, there's a special kind of network that's just a rock star at it. It's called a convolutional neural network, or CNN for short, and it has a couple of really clever tricks that make it perfect for dealing with pictures. So the first big trick is something called a kernel, or a filter. The best way to think about these is like tiny little magnifying glasses that are each trained to look for one very specific thing. You might have one kernel that's an expert at finding horizontal lines, another that only looks for vertical lines, and another that's looking for a certain shade of green. They just slide all over the image, hunting for their one special feature.
And this is what one of those kernels actually looks like. It's literally just a little box of numbers. As this box passes over the pixels of an image, it does a little bit of math. And for a kernel like this one, an edge detection kernel, the result is that it makes the edges pop out. So you end up with a new image that's basically just a sketch of the original.
Okay, so after all those kernels find a bazillion different features, edges, curves, colors, the network has a ton of information. To keep things manageable, it uses a technique called pooling. This is basically a way of shrinking things down while keeping the most important bits. Max pooling, for instance, looks at a little square of the image and just keeps the strongest signal, which is great for sharp details. Average pooling, on the other hand, kind of blurs things together by taking the average, giving a more general overview. Now, a lot of these ideas have been floating around for years, even decades. But then there was this moment, this tipping point, when everything just clicked into place and launched an absolute revolution in AI. It really wasn't just one thing. It was this perfect storm. You had, for the first time, these enormous data sets, like ImageNet, with millions of labeled images to practice on. At the same time, we got super powerful computer chips, GPUs, that could do all the math incredibly fast. And finally, researchers came up with new ways to build much, much deeper networks. All three of these things had to happen at once.
And this number right here, this is what blew everyone's minds. In 2012, a CNN called AlexNet just demolished the competition in the big annual ImageNet challenge. It had an error rate of 15.3%. The runner-up wasn't even close. This was a huge, shocking leap forward. It was the moment everyone in the field looked up and said, okay, this deep learning stuff is the real deal.
Okay, but here's where the story takes a really weird turn. You'd think that because these networks are so incredibly good at recognizing images, they must be seeing the world kind of like we do, right? Well, it turns out that's not true. Not at all.
So some researchers got curious and set up a brilliant little experiment. They wanted to know, what are these AI systems really looking at? Are they focused on the overall shape of an object, or are they paying more attention to its texture, its surface pattern? So they did this. They created these bizarre images. For example, they took the shape of a cat, but gave it the texture of elephant skin. What happened? Well, a human looks at that and immediately says, that's a weird-looking cat. But the AI, it completely ignored the cat shape and confidently called it an elephant. The results were just mind-boggling. It showed that the AI had learned a kind of shortcut. It was relying almost entirely on texture, not shape, because that was an easier pattern to learn. It really proved that these things perceive the world in a way that's totally alien to us. And that leaves us with this really big, fascinating question. I mean, if an AI can become a master at a task, even better than a human, without seeing the world the way we do, what does that really mean for the future of intelligence? It seems we're not just building a machine that thinks like us, only faster. We're actually creating a powerful, and maybe a fundamentally alien, new kind of mind.